Interpolation is one of the most important concepts in this class, and it has to do with being able to approximate data points that we don't actually know. So just as a simple example, I've got a table here of various angles in degrees from 0 to 90, and the sine of that angle is written here in this column. And let's say that we would like to know what the sine of 25 degrees is. Now, of course, we know sine is on the calculator, so we could just type in 25 and hit sine and we would have the answer. But what if this was some function that's not available in the calculator? How would you be able to estimate what sine of 25 is just based on this table? There's a way to do that, and it's called interpolation. So we basically look at the value just below 25 and the value just above 25. So in this case, we're looking at the sine of 20 and sine of 40. If we take some value that's in between those, we can get reasonably close to what the actual value is. Now, we limit ourselves to a type of interpolation called linear interpolation. So let me give you an idea of what that means. First, I'm going to draw a graph of what the sine curve looks like. So sine starts at 0, 0, and at 90 degrees it has the value 1. That's its maximum. At 180 degrees it goes back to 0. At 270 it's at -1, and at 360 it's back to 0. And it's sort of this smooth curve that looks something like this. You've probably seen this figure before. It's like a sinusoidal wave. Now, obviously this curve is nothing like a straight line. However, if you consider 2 points that are nearby on the curve, like if you take a point right there and a point right there, you can see that just that little piece looks fairly close to a straight line. The closer those two values are, the more straight line approximates the curve, and that's true of all curves that we're going to investigate anyway. So even though we only know this table, we only know 7 angles on this table from 0 to 90 degrees, you could imagine splitting up that little section into 7 separate lines, and it would fairly closely approximate the shape of that curve. So that's kind of the idea behind linear interpolation. As long as you have enough points to capture the behavior of the function, you can get fairly close just with linear interpolation. You don't need to do more advanced interpolation. So we're going to do an example of how you would calculate sine of 25 using interpolation. So what I like to do is make a table. So we have our angle here, 20. 25 is our unknown angle, and we also know 40. So we know sine of 20 is 0.342. We know sine of 40 is 0.642. And the unknown here is x. We don't know the sine of 25. So we're going to use these other 5 values to figure out what x is. And there's a formula that lets us do that. I'm actually going to call that unknown yt just so I match what you're seeing in my notes. So yt is my unknown value. We can look at this as like a table. So I've got a 2-column table with 3 rows. And as you go through this example, you should be thinking about how you would implement this in Excel, because that's going to be the first Excel project, is doing interpolation. So if I have a setup like this, more generally, I would have a table again, 2 columns, 3 rows. And I name these values x1, x2, xt, and y1, yt, y2. So for every x, there's a corresponding y. In this case, for every angle, there's a corresponding sine of that angle. And I have the two known points are 0.1 and 0.2, and t is the unknown. So for these interpolation problems, we know 5 of these values, but we don't know this 6th value. That's what we're trying to find. So the formula can be written like this. Yt is equal to y1 plus, in parentheses, y2 minus y1 times the fraction xt minus x1 divided by x2 minus x1. So this is kind of a messy formula. You'll notice that yt is the unknown, everything else is known, so you can solve this for yt. Basically what we're doing is we're checking to see, if we imagine 20 is at 0% of this line and 40 is at 100% of that line, what percentage along the line is 25? Well, we can see that there's 20 units between 20 and 40. And so 25 is 5 units from 20, therefore 25 is a quarter of the way from 20 to 40. That's this part here. You're basically determining what percentage along the line is the new point. This part here is checking the range for the y values, so you're subtracting the 0.642 minus the 0.342. So what you're doing here is you're taking 25% of the entire range from y1 to y2, and then you're just adding y1 to get your yt point. So that's kind of a way to interpret how this formula works. You can kind of see how this equation was derived. Now if you go through the math, and you should do that on your own, you'll get yt is equal to 0.417. So if you plug all those values into this formula, you'll get yt is equal to 0.417. Now the true value of sine of 25 degrees is about 0.423. So you can see we're a little bit off because, again, this is just a linear approximation of a nonlinear function. But that's okay. You can see that we're fairly close. An additional exercise that's good to know how to do is calculate percent error. So let's calculate exactly how close to the correct answer we got in terms of percent error. So we take our guess value, which is 0.417. That's our approximation. We subtract the true value, which is 0.423. And we divide by the true value, which is 0.423. And we arrive at negative 1.4%. So in this case, for this example, our approximation was a little bit over 1% away from the true answer. So that's pretty good. If we can get within 1% when we're using interpolation in the real world, we're very happy with that result. Now I want to point out to you that sometimes you're going to get functions where the values, the x values could be negative values, and the y values could be negative, and they could even, in this case, both are increasing. From 0 to 90 is an increase, and from 0 to 1 is an increase. But sometimes the x value is increasing and the y value decreases, or the x value decreases and the y value increases. What I'm trying to tell you is that none of those things matter as long as you set up your table properly. So just take the table as it is and put the values in the same order they appear in the table. So here I've got 20, 25, 40, and here I've got 0.342, my unknown, and 0.642. So whatever those values are, just put them in the same place in this table and use these variables, and I promise you the math will work out. A common mistake that some people try to do is, if they see a negative value in here, or if they see that things are going in the opposite direction, they'll try to reverse some things in this formula to try and make it work out, and then use positive numbers. Don't try to do that. You'll just you'll mess it up 9 times out of 10. So just use this exact formula in this table method, and you'll be fine. Okay, let's look at a somewhat more complex example of interpolation. So here we've got a sample table which shows water discharge in gallons per minute as a function of nozzle diameter and pressure. So these numbers here, these 9 numbers, just draw a box around them. So for example, 0.37 is the water discharge in gallons per minute if you have a nozzle diameter of 0.0625 inches and a pressure of 10 psi. So each of these numbers is a function of two variables, the nozzle diameter and the pressure. In addition, this table also shows the discharge velocity of the water in feet per second, and that's purely a function of pressure. So you can see here I have the pressure, so for 10 psi I have a discharge velocity of 38.6 feet per second. So this table is showing a lot of different information. And you should be try to get comfortable looking at this type of a table, because we're going to see many examples of this type of table as we go through this term when we look at fans and pumps. So the example problem we're going to do now is, let's say we want to know the water discharge at 12 psi and a nozzle diameter is 0.1 inches. 12 psi does not appear in this table, and neither does 0.1 inches. It'd be somewhere in between here. 0.1 is somewhere in between 0.065 and 0.125, and 12 psi is between 10 and 15. So we're going to actually have to do a technique called double interpolation in order to estimate what that value should be. Now, this is where interpolation becomes very useful, because as you can see, there's no button on your calculator to calculate water discharge rate in gallons per minute. So this is a function that your calculator has no idea about. So we have to do some sort of interpolation technique in order to estimate that value. So the technique I like to use again is setting up a table. Okay, so here I've drawn the setup of the problem. We can see that I've put the pressure column here. 10 is a known value on the table. There's 10. And I've got 15. There's 15. My new pressure is 12. That's from the question. Similarly, for nozzle diameter, I have 0.0625, 0.0125, or 0.125. And then my new nozzle diameter is 0.1. Then I just fill in the known values. So this value, 0.37, 1.48, 1.81, and 0.45, they go into the corners of the table. So you can see this table, I've got stuff on the top, stuff on the side, and then 9 values right here in the middle. 4 of those values I know. These other 5 values I don't know. The only one I'm interested in is yt, but to figure out yt, I have to either figure out A1 and A2 or B1 and B2. I don't need both. You can see that if I just look over here at B1 for a moment, I've got 10, 12, 15, 0.37, B1, and 0.45. If you were paying attention, you should notice that that looks like a single interpolation problem right there. So I could do interpolation on these 5 numbers to figure out what B1 should be. Same thing for B2. I could do 10, 12, 15, 1.48, 1.81, do an interpolation on those numbers to figure out B2. Once I have B1 and B2, I can interpolate between those and the top numbers here, 0.0625, 0.1, and 0.125. That's one way to do it. I could also solve for A1 and A2 and then interpolate between them to get yt. So there's 2 ways to solve this problem, but if you were paying attention to what I just said, you'll notice that we have to do 3 interpolations. So even though the technique is called double interpolation, it's kind of a misnomer because you actually have to do 3 interpolations to solve a double interpolation. Now, in the notes, I go through this example in detail and give you the equations, but the final answer is going to be yt equals 1.128. So again, this is something that you can do in two ways. You can do by solving the A's or by solving the B's, whichever way is more comfortable. A good practice when you're first starting out is to solve it both ways and make sure you get the same answer. Because if you do, there's a very good chance that you're doing it correctly. So for the homework assignment, you're going to have to do interpolation problems like this. I would practice doing them by hand, and then the first Excel project you're going to learn how to do in Excel. But I think you'll find the Excel project much easier if you master being able to do it by hand first. Okay, finally I want to concentrate on a related topic, which is called extrapolation. So far we've talked about interpolation, where I've got a known point here and here, and I want to know what happens at this point here. What is the value at x? That's interpolation. I have two known points that surround the unknown point. I use those two known points to estimate x. Extrapolation is where you have known point, maybe you have a few of them, and then your unknown is beyond the edge of your known data. So I don't have another known value on the other side of x. X is outside the bounds of all my known information. So this is called extrapolation. It's the exact same thing as interpolation, it's just that my unknown is outside the bounds of my known data. The good thing about extrapolation is the formula for interpolation is exactly the same as the formula for extrapolation. You choose this point right here and this point right here, the two closest points, and use that formula I showed you before for interpolation, and then you can find x. Problem with extrapolation is that it's inherently less accurate than interpolation because you're beyond your known data. You don't have the constraint of being in between two known data points. So extrapolation, you typically see a greater error than you do with interpolation, which makes sense, right? Because if you're, exceeding the bounds of the stuff that you know, you're bound to have more errors. Extrapolation we run into not as commonly in energy management as we do for interpolation, because typically we know, like for example, if we know something about a fan, we know what it does at full power, we know what it does at zero power, and we want to find what happens in between. We don't really need to know what happens beyond full power in general. So we don't run into extrapolation very often, but you should know what it is and how to do it. Just know that the formula is the same as for interpolation.